One property of a distribution is shape. Another property of a distribution is center. A third property is distribution variability. Variability refers to the spread of scores. Here are three histograms picturing three distributions. I've purposefully chosen samples that are of equal size, 19 cases, and that have the same center. The median and means are 10 for all three distributions. All three of these are symmetrical distributions. So what is different about these three distributions? The difference is the variability of the scores. In the first example, there is little variability. If there was no variability, every score would be the same. The scores are not all the same, but all the scores are close to 10. In the second distribution, there's more variability. Scores are evenly spread all the way from 2 to 18. In the third example, there's even more variability. The scores here are also spread from 2 to 18, but most scores are near the ends of the distribution. This means that all scores are far away from the middle score of 10, and the scores on the two ends are quite a distance from each other. Just as we have statistics for the center of the distribution, we have statistics to help us understand variability. The first variability statistic is the range. The range identifies the minimum and maximum scores in the sample. Here's a set of scores. The minimum score is 3. The maximum score is 17. The range is from 3 to 17. Sometimes you will hear range defined as the maximum minus the minimum, but I personally never do this. I consider it more informative to say that the range is from 3 to 17 than to say that the range is 14. Let's look at the range for each of our three examples. In the first example, the range is from 8 to 12. In the second example, the range is from 2 to 18, so this indicates more spread of scores than in the first example. Yet in the third example, the range is also from 2 to 18. Yet this distribution has more variability than the second example. The problem here is that the range is based solely on two scores in the sample, the minimum score and the maximum score. Thus, it has limited value if we want to account for the variability of all scores. The second variability statistic can help us out. That's the standard deviation. It is the average or typical deviation from the mean. Let's explore the concept of standard deviation, starting with the definition of deviation. In statistics, we often talk about deviation from the mean, and here's the formula. It's simple. We subtract the mean from the score to find out how far away the score is from the mean. Here's a set of scores that have a mean of 20. I've also listed the deviations for these scores. 25 is 5 above 20, so the deviation is 5. The score of 20 is hanging out with its buddies at the y-bar, so the deviation is 0. The score of 15 is 5 points away from the mean, but it's below the mean, so the deviation score is -5. The absolute value of a deviation, that is the deviation without the sign, tells us how far away the score is from the mean, but the sign tells us whether the score is above or below the mean. Here's an interesting fact about deviation scores. Their sum is 0. The mean of deviation scores is also 0. When we talk about average deviation from the mean, we might be inclined to think that we can simply average deviation scores, but we can't. Well, we can, but that would not be a very helpful statistic since it would always be 0. Here's the formula for standard deviation. Ominous looking, I know, but let's break it down bit by bit. On the left side of the equal sign is an S. That's the symbol we use for standard deviation. The Y subscript indicates that this is the standard deviation for the scores that we called Y. On the right side of the equal sign, inside the parentheses in the numerator of the fraction, is deviation. The deviations are being squared. Aha! If we square deviation scores, they will all be positive, so they won't cancel themselves out when we add them up like the deviation scores do. We now take the average of the squared deviations, then we calculate the square root to go back to our original units. For example, if I square deviation scores that have a measurement of feet, I'm going to end up with square feet. But when I take the square root, we'll be back to feet, the original units. So far, so good? No, you shout. Wait a minute. You didn't really take the average of squared deviations because you didn't divide by n. You divide it by n minus 1. It's going to take a short little side trip to explain this. I want to introduce you to the concept of degrees of freedom. We use this quite a bit in statistics. Degrees of freedom are the number of units in our sample that give us new information. It is based on sample size and the number of statistics we've already calculated. All right, let's keep it simple and consider a sample of size 3. I'm going to place the scores for each unit in the sample on these 3 lines. I have a score of 3, a score of 5, and what's the third score? We don't know. It could be anything. In other words, for this sample of size 3, all 3 units provide us new information. There are 3 degrees of freedom. When we calculate the mean for this sample, we add up the scores and we divide by 3. We do this because all 3 scores provide information. For the mean, the sample size n is equal to the degrees of freedom. All right, by now you may be totally confused, but stick with me a moment. Suppose I have already calculated the mean and I tell you that it is 6. Now, can you tell me what the third score is? You may have to reflect on this a moment because it's like solving a little puzzle, but you can figure this out. If there are 3 scores, and if the mean is 6, the sum of the 3 scores must be 18 because 18 divided by 3 is 6. Now, if the sum of the scores is 18, that missing score must be a 10. Notice what happened? When I told you that the mean is 6, you could figure out the third score. So the third score did not give you any information that you did not already know. In this case, because we've already calculated the mean, only 2 of the scores give us new information. So the degrees of freedom are 2 after we have calculated the mean. Back to our standard deviation formula. If we are calculating deviations, as we do in the numerator of this formula, then we first must calculate the mean. If we have calculated the mean, we no longer have n degrees of freedom. Rather, we have n minus 1 degrees of freedom. You now know something most of your friends probably don't know. Most people think that taking an average means you divide by n, but in fact, to get an accurate average, you divide by the degrees of freedom. In the case of the mean, that is n. In the case of the standard deviation, which requires we've already calculated the mean, that is n minus 1. We really are taking the average of the squared deviations. The square root then puts us back in our original units of measurement. For the set of scores here, the mean is 9.73, The standard deviation is 4.43. This tells us that we shouldn't be surprised if we find a score that is about 4.5 units away from the mean. That's a typical deviation. The standard deviation is especially useful for comparing distributions. Look at our original 3 examples. The first sample has a standard deviation of 1.33. The second has a standard deviation of 5.16. The third has a standard deviation of 7.57. Do you see how calculating the standard deviation has helped us understand relative variability within these 3 samples? The third sample has substantially more variability, almost 6 times more than the first sample. It also has more variability than the second sample, even though the ranges for these samples are the same. Knowing distribution shape, center, and variability helps us understand a lot about the distribution. Even more importantly, these characteristics will help us compare distributions. This is something we will do often when addressing research questions.